All right, welcome back for another episode of Connie 352. Today we're going to get into an introduction into plumbing and piping. Some things that you might need before we get started. Why don't you pull up the schedule? We'll talk about it really briefly. Also, the plumbing handout, we're going to have that. Looks like this. Okay. All right, it's this page here. I'm also going to be pulling up some web pages, some images off of Google. I put a couple of links on the announcements board, so if you want to pause and find those are good for reading. We're not going to get into terrible detail on any of those, but those would be good information for you to check out and review later. All right, so let's get started. Let's take a look at that schedule. Today, here we are at Thursday, the 26th of March, Intro to Plumbing and Piping. By this point, I hope you've all watched the lectures on LEED. I hope those were good. Those are my first attempts, so they may be a little bit rough. Hopefully, I'll get better at this as we go. But anyway, that was a start of our lectures here online. Today, plumbing and piping. Next week is when we'll actually start doing the calculations, and I'll start assigning some homework. I'm just so you know, I'm having some thoughts on homework. A few things. One, the homework for the small town office building. What I'm thinking of doing is that I really do not want to try to find a way to mail back everybody's homework, and I don't want you to come in and pick it up. So what I think I'm going to do is I'm going to post the solution so that you can look at the solution and see what your answer should have been. All right. Then for the plumbing homeworks, what I'm thinking of doing is assigning the homeworks, and then after they're due, I will post the solutions. And here's what I want you to do. All right, it's time for a little honesty. What I want you to do is do the homework honestly, and then take the answer key and grade your own. Grade your own. See if what you did makes sense. See if what you did gets the answer. Now, I am going to stop grading homework. I'm going to stop grading homework. I want you to do it, though, because here's why. The reason I have you do homework is that it makes sure that you understand the topic. And the homework prepares you for the exams. The homework also prepares you for the final projects. So with that in mind, I want you to make an honest attempt at the homework, but we're not going to grade it, and we're not going to have you scan it and send it in. But I want you to do it just so that you know what you're doing. All right. With that in mind, let's switch gears and let's get to water and water quality. All right. Water quality. What does water quality mean? Well, as we're talking about water quality, okay, water quality refers to the chemical, physical, and biological characteristics of water. We are predominantly going to be talking about water quality as it refers to drinking water in this class. So we're only going to be talking about how do I take raw water. Raw water comes from any source. Raw water could come from a river. Raw water could come from rainwater. Raw water could come from an aquifer. It can even come from the ocean. But how do I take that raw water and turn it into usable, drinkable, potable water? And obviously, the cleaner the water source is that you start with, the less energy will have to be expended on cleaning that up. And that's why you don't see a whole lot of seawater being used as the basis for producing potable water. Turning seawater into potable water is a very energy intensive process. Look, no matter what it is, turning raw water into a drinking water is an energy intensive process. There's only so many ways that you can do it. You can filter it and treat it. You can put it through something called a reverse osmosis system. A reverse osmosis system is not a filter, but it does separate contaminants from the pure water. I'll show you how that works in just a second. And then we can also distill water. Distilling is probably the easiest to understand, but it's the most energy intensive option. Distilling is where you boil it off and then let that steam condense, and then you have only pure water left over. It's a very simple process, simple to understand, but very energy intensive. So let's just take a look at what water quality is and why does it matter? All right, obviously we have to get the water pure enough to drink. But you can drink drinkable water isn't pure. It isn't 100% clean. If we take the water coming out of any municipal water supply, it's going to have suspended solids in it. It's going to have chemicals in it. The question is, have we controlled those suspended solids and chemicals to the point where what someone's drinking isn't dangerous? That doesn't necessarily mean it's clean. And different cities are going to have very, very different levels of water quality. For example, let's just use an area that I'm familiar with, the Des Moines Municipal Water Supply. The city of Des Moines itself has very, very good water quality. The city of West Des Moines is not as good. It has a lot more suspended solids in it. Suspended solids. What are suspended solids? Very frequently, they're calcium, lime, rust. Basically anything that didn't get trapped by the purification process. And like I said, trying to get it completely pure would be incredibly expensive. So that's not going to be done in a municipal water supply. So it's a trade-off. It's like, well, how much money do you spend and how on the water treatment system, both first cost and then energy costs thereafter, versus how much damage is that going to cause over years? For example, when I was a practicing consulting engineer in the Des Moines area and from 2000 to 2005, the average life expectancy of a domestic water heater in West Des Moines was about 5, maybe 8 years. And what would happen is, and water heaters are the worst because as you take that input water and just heat it, you get this left behind. And not just in water heaters. This is actually a pipe from just a water line going to a residence. In West Des Moines, Valley High School, when we redid Valley High School in 2004, they cut out the old pipe that was an 8-inch wide pipe. And when they cut it out, it was actually even worse than this picture. There was only, out of that 8-inch wide pipe, there was maybe 2 to 3 inches of clear space through the center of this that water was going through. And I thought maybe that water pipe was original to the building, and the building was built in 1969, and we did this in 2004 or so. So you're looking at, 30, I thought it was over 30 years old. And the building maintenance manager for for West Des Moines School said, no, that's only about 10 years old. And apparently I learned that was fairly common in city areas where they just don't spend as much money on water treatment. Now, the city of Des Moines does a really good job of water treatment, and they have a lot more extensive facility. So how do we take raw water from a river like the Des Moines River or from an aquifer that we would drill down to? How do we take that water and turn it into something cleaner? All right. So here's the basics of this. And let's go from left to right here, where we have inlet water, wherever source that is, aquifer, reservoir, stream, lake, river, whatever it is. So water comes in and it goes through a coarse filter. A lot of times these filters are sand filters. Coarse and fine filters just has to do with the particulate that filter can trap. So it's filtering out the suspended solids. It does not remove things like bacteria or those types of contaminants. So goes through a coarse filter and then goes through a sediment tank. Think of a sediment tank as like a big tank that the water is moving through it very, very slowly, and that water is allowed to sit. The slower that water is moving, the greater the chance that your sedimentation will naturally settle to the bottom where it can be more easily removed. After it goes through the sediment tank, it goes through a fine filter where we're able to filter out even finer particles and suspended solids. Now, notice I said suspended solids, not necessarily things in solution. That requires something even finer, right? But then we go to, we're going to do some chemical treatment to it. We're going to add chlorine. That's where we'd also add fluoride. It's where we might also try to remove nitrates or have some type of chemical that would neutralize other contaminants. And then from there, it's going to go to a storage tank. Think like a above ground water tower. And then from there, it goes to homes and factories. Now, let's kind of zoom in. This is a little bit more, this is the schematic for the Des Moines system. Comes from the river, right? Now, this one has a sedimentation tank at first, okay? And then we have a mixing chamber where we add some chemicals to it, softening basin where a water softener is not a water filter. All a water softener does is exchange ions. In other words, it exchanges, say, like calcium for something like a salt. It exchanges these ions because we're trying to remove, calcium has a nasty habit of forming like a hard scale on water heater elements or on your dishes, even on glass or silverware. So an ion exchanger or a salt system is just going to exchange ions. And then we go to this big sand filter. And then for Des Moines, we also have a nitrate, that's down here in the bottom, a nitrate removal facility. And that actually is a pretty big point of contention in the state of Iowa, because a lot of the nitrates that are in the Des Moines River come from farm water runoff. And it's kind of a controversy over who's responsible for paying for the removal of these nitrates from water systems. And in fact, the city of Des Moines here years ago went so far as to sue some of the counties in the northern part of the state, blaming them for nitrate runoff into the Des Moines River. But that's an issue for politics. If you're interested in that, you could Google some of those articles, find out a little bit about the history of water quality and the arguments between cities that are removing these nitrates and farm communities that are blamed for putting the nitrates into the water supply from runoff from fields. But let's skip ahead to, well, how does this idea of a sand filter work? Now, this is an image of a simple sand filter that you might see in a pool, like a swimming pool, right? Where water will come in here at this valve, and it'll come in at the top of the sand filter. And then the pump pushes water down through the sand and then down. It's hard to see on this picture, but there are some pipes at the very bottom of this. All right, that's what these are. You can't see the sand in this image, but water comes in at the top and then gets pushed through the filter media, the sand, grabs a lot of those particles, and then that water leaves through these tubes at the bottom that are buried in sand. And then on this image, it comes out the side there and goes to that three-way valve. Now, this three-way valve is important, and actually it's probably not a three-way valve. It might very well be like a 4 or 5-way valve. This valve selects the direction that water is going to, because normally water comes in here and out the bottom. But as that sand media picks up, and in a pool, it's going to pick up dust and dirt and other contaminants. it's going to grab those in the sand filter, but it can't just keep adding and adding and adding dirt to the sand filter. Eventually, it's going to get clogged and it won't allow water going through it very easily. What you have to do is you have to periodically backwash this sand bed, and that's the purpose of this valve. It has the ability to change the order so incoming water can get pushed backwards through the media and then out the top, and there's another pipe on the back of this that takes it to a dump connection. In other words, it's going to take that backwash and then dump it to the out of the pool, dump it to like a sanitary sewer line, or maybe just discharge it to grade on a backyard pool. So it's just going to dump that water that contains the contaminants out of there. Now, notice the penalty that you pay here is, one, a lot of pumping energy, but two, with a sand filter, you use a lot of energy pumping water through this, both in normal operation and in backwash mode. But two, it costs you, you're losing water. Every time you backwash, you're using this input water to get rid of the contaminants, and you're dumping that water away. There's really no way around that. I mean, any of the either filtration or even reverse osmosis type of systems uses water to carry away the contaminants. So you are taking water and getting rid of it. And this is just a different illustration. It kind of shows the cutaway view a little bit better, but you're getting rid of that water and dumping it out. All right. Well, that's fine for a pool-sized system, but what about a system big enough for, say, an entire city? Here's one where these are large sand beds that water gets forced through in a citywide system. Right? Anytime these are all examples of water treatment facilities, like big sand beds that water gets forced through. Now, they do make systems in between this. You know, here's one inside of a facility. These are all sand beds, and then they're in the process of getting backwashed. They also make ones like for a hospital or a city that wants to take their water and purify it a little bit more. You can set up your own building-size sand bed or sand filter system to purify water like in a building. So that's what these systems are. Right now, how does this backwash process work? All right. The important thing when you backwash, and I just started this video here, it's in the process of backwashing right now. They pump water the wrong way from the bottom to the top, which will lift and carry away all those contaminants. A system for like a municipal system might also use compressed air to help bubble through this sand and remove some of these impurities coming out the top here. It showed the contaminants. And then once it's clean, they'll switch it back to the normal operation. Here's a municipal system. So this filter is dirty. In other words, they've been forcing water through it in the top and out the bottom for a long period of time. And they said, okay, we've gotten it too dirty. Here at first, what they're going to do is they're going to air blow through the bottom. You see it starts to bubble here. They are forcing compressed air through the bottom to kind of agitate that sand media and the dirt and contaminants that have been trapped there to break that loose, so that in the next phase, when they start in step 2, they're going to start pumping water through it to carry the contaminants away. And here, let's just skip ahead a little bit. Right, they're still blowing air through this. Notice how it agitates that sand greatly. Right, they're going to do that for a couple of minutes, and then they're going to combine air and water to pump the wash, to wash that layer of media. They're going to pump it through there and really, really wash that media. And then Notice how it overflows. The dirty stuff and the excess water is going over the sides. Ideally, it would take the dust and dirt and particles, but not a whole lot of the sand out of it. Sand being heavier should stay put. So they're going to wash that layer of media, and they're going to do this for several minutes. Let's fast forward. They're going to stop the air, and now they're going to continue water pumping. That's going to be the last part for rinsing all the dust for about 7 minutes in this particular bed until the water is clean. Notice here on the sides as this pours over, it's very, very brown. That's all the sediment that is getting washed out and away from the sand basin. So this has to be done periodically. How often does this have to be done, you might ask? Well, that depends on how clean is your input water supply. Typically, water coming from an aquifer like a well is usually a lot cleaner than water from a river. And water from like a reservoir lake that you might see near a town, like my hometown had a reservoir beside it, where it would fill up from a local stream, but they wanted a big reservoir to be able to pump out of that because they're kind of using that reservoir as a settling basin. But the problem with a reservoir is, well, I mean, it has organics in it, leaves, bugs, it has ducks, it has fish, it has all these typical organics, and all of that is going to have to be filtered out. And then once filtered, it's going to have to be purified, and that's where we'd add like some type of a chlorine to purify it. So here in this, they're still rinsing, and eventually it'll start getting cleaner and cleaner. And once the process is stopped, right, you'll see the effluent that comes out of there is a lot cleaner. And then in the bottom, you see it still looks kind of brown, but that's because of the sand that you're seeing in the filter itself. And then the process is stopped, and then it's back to filtration mode. You see over here at the edge, this is actually, kind of pretty clean down to that sand layer. All right. Okay, so that's the way, the basic of the filters. Now, you can also buy cartridge filters. The reason people like to use sand and municipalities like to use sand is that it's a very cost-effective filter. You can clean it and reuse it and reuse it and reuse it. Like a cartridge filter, those systems, once that cartridge is contaminated, most of them have to be thrown away. So they're not terribly cost effective to do on a large scale. They might be fine for, say, if you've got to filter water, maybe you just want a purified drinking water source, or maybe for lab work or something like that. A typical cartridge filter might work for that, but for a drinking water supply in the sheer volume that we were talking about, cartridge filters aren't terribly practical, and that's why you get these sand bed filters. All right, what if you need something more pure than that? All right, how do I purify water to levels that just a traditional cartridge filter or sand filter just can't do? The way to do that is a process called distillation, where we take, it's a very, very simple process. I take a tank of water, add some heat to it, and boil it. That steam leaves, and it goes through a cooling tank where that water cools back down, and the effluent, and maybe they put an activated carbon filter at the end of this, that guarantees that the water that leaves that comes in the storage tank, and it is truly pure. Way more pure than you might get from simply filtering water. Now, you can distill it in something like this. You could get a more automated system. Maybe you'll see something like this in a hospital, or for lab work. Once again, distillation systems. The downside of distillation systems is that they are very, very, very energy intensive. We've got to take all of that water and add enough energy to it to flash it to steam, and then we just condense it again. Most of the times, these systems aren't used for the sheer cost that it's going to take to purify the water. Now, there are some exceptions to that. What I've seen is years ago, I helped work on a cogen plant for the Kingdom of Bahrain. What a cogen plant is let's say that you have a power plant and you're already making steam. Let's say that you're already making steam from a power plant, and you have waste steam anyway that you need to condense, like after it goes through a turbine for a power plant. Here we go. All right. Well, what do you do with this steam? You're just going to condense it and pump it back to the boiler anyway. All right. And I know this is a little bit of a complicated picture, but what I wanted to show you here is that after it goes through the turbine, we could use this hot steam not to drink, but to put it through a heat exchanger and to boil raw water, or at least preheat it a long ways, and boil that water, or at least get it very, very close to boiling, so that it could be condensed and turned into drinking water. And that's what the Kingdom of Bahrain does in their power plant. Since they're making electricity, they have steam, and they live right next to an ocean without a whole lot of natural water supplies. It makes a lot of sense for them and for countries like them. So you might see a cogen plant as part of a power plant if it's located fairly close to the ocean. But what if that's not an option? All right, what I want to talk about is something called reverse osmosis. Reverse osmosis, it's not really a filter. All right. Sometimes people think of reverse osmosis as just a better filtration system. It's not. The key to reverse osmosis is right here in this picture. All right. What you do is you pass this inlet water, right? Incoming water is coming in here, and it goes through this cartridge. And you'll see it's like forcing water through here. Some of it gets rejected and takes the contaminants with it, but the purified water comes out after it goes through these various layers. And what's happening, if you look at this blow up here, the membrane for this reverse osmosis system is very, 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 very thin and has very, very small holes through it. These holes are a fraction of a micrometer. All right, 0.0005 micrometers. Very, very small. Smaller than bacteria. Smaller than blood cells. That's what these circles are showing. The reverse osmosis membrane pore is very, very small, so that things like contaminants, even bacteria, cannot make it through these holes in the membrane. They're, in fact, larger molecules like a sodium ion or calcium ion or magnesium ions. Those are too large to get through these. Now, pure water can make it, but these other things can't. So the outlet of this is simply pure water. Now, this is way more energy efficient than distilling water. You just have all the pumping energy. However, the pumping energy is significant. Can this be done? This is usually done on like a small scale. You might see something like this in a lab or on a countertop, that type of a thing. You might see it, in small scale. Maybe even there's even home systems in small scale that could do reverse osmosis and makes really clean water. It's just they're expensive, and they do require maintenance, but they work well. Can you do it for a whole municipality? I'm going to say yes, but I'm going to caveat that with these systems are pretty expensive. On the announcements, I hope you already saw for the announcements for this lecture a couple of links, and I'll let you look through this. This is one of the few desalination plants in the country that are in service using reverse osmosis. This is a desalination plant in Carlsbad, California. The reason this plant was put online in 2015, notice the date. 2015 is exactly the same time that we were talking about the height of the California water crisis. This system wasn't really cost effective until the water crisis got there. Now, it took something like a decade to design and build this system. And now they claim that this system puts out water at around 10 cents a gallon, which is pretty good. Okay? You can buy purified water in a gallon jug at around 80 cents or $1. So this is obviously much better, but a lot of that cost of the purified water you're buying in a gallon jug is the jug and the bottling and the distribution cost, right? So yes, this is cheaper. However, my personal opinion is, if you go down here, I'm sorry, not 10 cents. They're saying it's now half a penny per gallon. I don't think that cost includes the first cost of the plant, to be honest. I'm not sure on that, right? I want you to, if you're interested in the subject, you might want to read through some of these. Like I said, I shared this link to the Carlsbad desalination plant. They're putting out, 50 million gallons per day, which sounds like a massive amount, but it's not when we talk about drinking water systems. I don't think this half a penny per gallon includes the first cost of the plant, if I remember right, because I want to say that they offset. They got some pretty major federal grants to offset the first cost of that. Yeah, see here. All right. They got a $100 million Department of Energy grant in addition to the costs that California put in, and I don't know what the total costs were. Just know that I'm not sure that half a penny per gallon reflects the entire life cycle cost of this plant. Anyway, but I'll let you research that and take a look at it. I just wanted you to know that there are some examples of this. Now, understand, one of the downsides of plants like this is that if you put this through a reverse osmosis system, remember back to this drawing where it shows dirty water being dumped, and they call it a brine solution, right? This is a reverse osmosis cartridge, and it's a simple one just for an RV. All right. This brine is dumped. Think of that as on a large scale. All of the contaminants, and this is what is important about selecting the appropriate water source. If you are using water from the ocean that's already brine, removing all of those contaminants and then dumping them somewhere, that brine becomes super concentrated. You need to be cautious, and what they didn't mention in any of those articles is that they've got to pump that water, that brine water, out far away from the shoreline. Otherwise, it's going to create like a dead zone along the ocean beach where nothing will be able to live. So it's got to get pumped out to the ocean and dumped. And I don't remember how far away the Carlsbad facility pumps their water out into the ocean, but it's quite a ways, so that it has a chance to mix with the ocean water and it doesn't create a super, super saturated area that not even ocean life could live in. So just understand, remember going back to the first law of thermodynamics, you can't get something for nothing. Reverse osmosis is just like that. One, you've got to pay to pump water through that cartridge. Two, you've got to pay to dispose of that brine water. And three, you got to be careful where you dispose of it, because it is super saturated salts, and that can have some adverse effects. All right. So here we go. Like I said, I'm going to put those links on the announcement. So if you get a chance, check that out. And I found this interesting. That Carlsbad desalination plant went into lockdown this last week. And by lockdown, they didn't shut it off. It's still working. They are putting their employees at 21-day shifts. They parked a bunch of RVs in the parking lot. They leave fresh food for them at the plant gates. They put washers and dryers so that they can do their own laundry, and using the desalinations plant kitchen and cafeteria. They're basically, for 21 days at a time, locking some employees in there to isolate them from the risk of infection, to make sure that the water plant continues to operate. I don't think that's unique to the Carlsbad desalination plant. I think City of Des Moines is doing the same thing with their water treatment plant, and other municipalities are doing that to their treatment plants as well. Because for sure, pure water is one of the critical jobs, and keeping those going is absolutely critical to our country. So just know that that's kind of happening. I thought that was just interesting to see. Now, I also included a link to this article. There's not a lot of pictures. I'm not going to go through it, but I want you to read it. Popular Science, and this was just in December of this past year, put out this interesting article about, to solve global water scarcity, we need to get more serious about desalination. Desalination uses a lot of energy, but so does transporting water across great distances, like to the large cities along the coastline, like San Diego, Los Angeles, those types of areas that are short on water. And the city of Los Angeles gets most of their water from the northern part of California and the Colorado River, just like Las Vegas gets it. So you have to understand that takes a lot of energy just to pump that water all the way to those cities. And what the drought there that ended in about 2016 showed us is that water is a very scarce commodity and very, very valuable. If we can get it from other areas other than inland areas, it would be beneficial for all of us. All right, so it's an interesting article. Read it yourself, but just remember that pure water, or at least water clean enough to drink, is a precious commodity. It is very energy intensive, and this is a issue that is going to get worse, not better. There is no, with increasing populations, I think pure water that's water pure enough to drink is as scarce, or maybe more scarce of a commodity than energy. It's something that we don't take a lot of, that we don't give a lot of thought to here in Iowa. But this is a worldwide issue, and in your careers, it's only going to get more and more important. So with that in mind, all right, let's continue our discussion, and let's get into the basics of domestic systems for buildings. And we are going to talk about, well, how does a trap work? How does a toilet work, and some of the different types? And then we'll actually get in the calculations next week. So let's get to plumbing. Now, the term plumbing, common convention is when you hear the term piping and you hear the term plumbing, usually what this means is we're going to refer to plumbing as domestic water systems. I don't mean domestic as in a residence. I mean even in a commercial building, the domestic systems. Domestic water and plumbing refers to water that comes in, we use it once, and then we dump it down the sanitary sewer. That is domestic water and plumbing systems. It is one use, and it's meant for drinking, flushing toilets, washing your hands, those types of applications. Piping refers to water used for an industrial purpose, for heating a building, cooling a building. Water and water pipes that where the water circulates and circulates and circulates, and we don't just dump it down the drain. We use it for some type of an industrial purpose, like heating a building. So it's not meant that these systems cross-connect, other than frequently piping systems are filled by the water in the domestic water system. But other than that, they're supposed to be completely separate. Now, you might look on a project and you might see some copper pipe, and it's the exact same copper pipe being used for the chill water system as it is being used for the plumbing system. Okay, it might be the same pipes, might be the same fittings, the same insulation. But when we talk plumbing, I'm talking about domestic water, and we talk piping, I'm talking about industrial purposes. So, with that out of the way, let's take a look at a simple trap on a sink or lavatory. The trap is this part down here. All right? The purpose of the trap is that it gives us a water seal that stays there so that we don't get sewer gas that's coming up going back through the fixture. Plumbing systems don't have water flowing through them all the time. And in fact, most of the time, they're just sitting there without any water moving through them at all. When they're just sitting there, this pipe still connects to the sewer system, so that air from the sewer system can come back through here if there isn't something to stop it. That's the purpose of this trap, this low point that traps water. Now, water has to be in there all the time for this to work. See this up here that goes up? That is referred to as the plumbing vent. The way this works is that plumbing vent goes through the roof of the building and vents up above the roof, so that air is always in the upside of this system, so that when this water flows through here, it doesn't siphon the water out of the trap. And I have a little video here to illustrate how this works. So here we have what's called the P-trap of a sink. No, it's not called a P-trap because it traps pee. It's called that because it's in the shape here of the letter P. So this trap, when nothing's flowing through it, sewer gas cannot get back through here to go back into the sink. So let's say you wash your hands. You've got some water flowing through it. With this air here, once the water stops flowing from the sink, that air breaks the siphon and prevents the water in the trap from getting siphoned through this and down into the sewer system. Now, in this part, you'll see up here, they've simulated this is clogged. Well, how would that be clogged? One common way, actually, in winter, is if ice was to form at that and prevent air from coming in. Or maybe some do-it-yourselfer didn't actually install it, or installed this too small, or didn't install it at all. Says, I don't see the purpose of this air pipe. So if that was clogged or non-existent, this is what would happen. Water would flow through there, and then it would get siphoned out of there when the water flow ended. Now, what would happen then is sewer gas would come back through there, and then obviously the room would smell. Another reason that could happen is if you have a fixture that doesn't get used very often. You know, like a sink in a closet, like a janitor's closet somewhere that isn't being used, or a shop. Maybe a floor drain that doesn't get a whole lot of water flow through it. Those can evaporate over time, and you can get those drying out, and then enough anyway that the water level gets below the bottom of that curve, and now sewer gas can get back through. The way you fix that is periodically put a little water down the floor drain. All right, now on the toilet, notice the toilet next to it. Let's say that that was clogged and somebody flushes a toilet. Now, the way the toilet works is you'll notice it's not vented over here at the toilet. Yes, it's connected to a vented line, but right here, the way this works is when water is flushed, notice that the tank is taller than the height of this loop seal. Once the toilet flows through there, it slowly fills back up, and that allows it to fill and not get siphoned through that trap normally when it's working properly. But notice on this illustration, if that vent is still blocked, the toilet won't get sewer gas going through it, but the sink will. So if you flush a toilet and then get sewer gas at a sink, it probably means the trap to that sink is blocked. Now this is a diagram of an S-trap. Older homes and commercial installations might have a trap that looks like this. The plumbing code will not allow you to put an S-trap in anymore. The idea was the S-trap made it harder, still formed that seal, and made it harder for it to siphon through there, but it still could and very frequently would. So if you have an older S-trap, you really need to vent the top of that S to make it work. This is a picture of a remodel fix of this. ProVent makes these. These are air intake vents that allow air to come in but not out. You just cut the pipe, add a little section here with a T, and put this ProVent. ProVent is a manufacturer's name. They're just one of many. And vent it this way. This may not be allowed by current plumbing codes, but I will tell you that they work. So now the plumbing code depends on what city you're in, and different codes apply to, different municipalities have different codes. Some of them do not allow the use of a ProVent. An example where you might see one of these is like an island sink, where you can't vent this top any other way because you just can't. You've got a sink in the middle of an island in the middle of the room, and there's no wall to put that vent line in. So you might see a ProVent in that type of a situation. All right, let's keep going. Another way that a trap might dry out. Let's say that this is a bathroom sink, and hair and other things get trapped down there. What hair can do is that it can act like a capillary function and slowly wick that water out of the trap to the point where the water level drops low enough that, especially in a house that sits open for a long period of time, water level can actually drop low enough so that sewer gas comes back through. In that case, you just need to clean the trap, maybe take it apart and remove the hair and whatever else might be in that trap to stop that from happening. All right. I'm going to talk a little bit about commercial water closets versus residential ones, and wall mount versus floor mount. Most of the time when we look at residential water closets, they're going to be a tank type of water closet. And this is the one that you're used to seeing in a home, where the outlet is on the bottom. It stores water in a tank behind the toilet bowl. And when you flush it, the water in this tank rushes through here, draws whatever's in the bowl through its trap there and into the sewer system. Now, the advantage of the tank system is that this is way cheaper than the commercial one I'm going to show you next. The first cost of these is much lower, and the size of the water connection to this is also much smaller. You can probably get a 1/2 inch or maybe even a 3/8 inch water connection to this toilet, and it can slowly fill up. Now, the downside is that this was not meant for commercial applications. This is not meant to have flush after flush after flush like would be in a house, right? I mean, it's meant for the sporadic use in a house, but not the continuous flushing like a commercial application might have. And in that case, what you need is a flush valve type of water closet. This one happens to be a floor mount. And notice, instead of the tank, it's replaced with a flush valve and a fairly large pipe. Notice, this pipe connection is probably inch to inch and a half. That's a pretty major water pipe connection. And the way this works is that when this is flushed, instead of the tank holding the volume and goes through the bowl that way, this allows a kind of a jet of water to pass through here. But you need a very large water connection to do this. Also, this is a lot more expensive piece of equipment than the tank type water closet. All right. You need to have sufficient water pressure, and we talk about water pressure later in the semester. You need to have at least 20 psi available to make this water valve work. That doesn't even include the pressure needed to get it to this tank. So there are some downsides to this, but this one is meant for continuous operation. It's meant for commercial use. It's meant to be flushed again and again and again, hundreds of times a day perhaps. So just know that that exists, or the difference exists, is that this is meant for continuous use, whereas the tank type ones are probably not. Now, this is a wall mount. You'll see this most commonly. These are going to be easier to install. And by that, I mean, you can put this on a carrier and you can have a lot easier piping installations. What you don't see here is here you see it on the wall, but you don't see the part behind it. You don't see the piping behind it. A wall-mounted water closet is not supported off of the wall. The wall is not holding that water closet in place. It's if you look behind it, this is a picture that removes that wall. This steel part behind there, that is the carrier. If we look at what that looks like without the water closet, here is a carrier. Notice the structural steel frame that rests onto the concrete, and you'll notice right here and right here, that's where they would actually put some concrete bolts to hold it down to the ground. That's what supports the weight of the carrier and whoever is sitting on it. These long bolts that extend through the wall, those are carrying the weight of it, and it clamps that fixture here to the wall on the other side, or to the support behind it. Here's a picture that they've done. Notice this is getting ready for a bathroom group where we have several all together. Notice these first four are the regular ones, and this last one, this fifth one, is quite a ways away. That's going to show where the handicapped toilet is. But the rest of these are all built without the wall actually being put there. The wall will come in later. Notice the domestic water pipe that goes along here, the top, that's a pretty large pipe. For a bathroom group like this, you might need a 2-inch water main, and each one of these would get like an inch or so pipe size. Also, notice here is the sanitary sewer. These are mounted so that the outlet of one goes through the next one and through the next one. They are piped in battery. In other words, one after another, and then there is only one connection right here. See this main plumbing stack? All 5 of these empty to this one main, and then that goes down to the next floor. And notice it comes from above, coming down. Also notice back here, hold on a second. Aha. This top copper pipe is the vent. It's this bottom copper pipe that goes to the flush valve. I had that wrong in a second earlier when I pointed to this as the water pipe. This is the vent pipe that comes off of each of these and then goes up to this vent stack. So notice, sanitary sewer goes down here, plumbing vent goes up here, water main comes in here and goes to a flush valve connection. See this copper pipe right here? So that when the plumber comes in to do the installation later, it will get connected to this pipe right there. And it has some like a chrome trim. That's just to make it look nice, more resistant to stains, and it'll look a little bit nicer for the part that you can see. And the rest of it is hidden behind this wall. All right, there's a view in AutoCAD, a little bit of a quick view in AutoCAD, and that's going to be what it looks like. Now, common thing now for plumbers is to build this in a shop and bring it to deliver it on site, all pre-piped, so that you only have to do a couple of connections and build it in the shop and prefabricate it as much as possible. Baker Group does this a lot, and then whoever's framing the walls would come in later and frame the walls in after the fact, right? Notice this blocking here. This is where you might see some wood blocking to give them some place to put grab bars, to give them a place to support some of these pipe hangers and that type of thing. That's why you might see wood framing in and around this these steel boards, something a little bit more rigid to support weight off of. All right. So what we're going to do is we are going to pause here, and next week, the Monday lecture, we'll start doing domestic water pipe calculations. So stand by for that, and I will see all of you next week. Also, do not forget to post final project questions. Later today, I have a teleconference with one of the groups that had some questions. I encourage you to set up, email me, set up some conference time so that we can get your questions answered and that sort of thing. I want to make sure that you've got all your questions answered for the final project. Normally we would do that in class, but obviously we're going to have to do that with teleconferencing. Also, be sure that you are checking those discussion boards. They're on Canvas. All right, we're going to pause here, and I will see you next week.